Welcome to the course on two-dimensional signal processing, principles and practices. In this lecture, we'll do the Fourier analysis of two-dimensional signals, especially the discrete space Fourier transform. That is the DTFT, what we had learnt in the previous lecture. That is, by x of omega, the spectrum can be obtained from the summation of this x of n, the e power minus j omega n. The samples are known in 1D. Then you can get this spectrum as DTFT. This spectrum is going to be discrete one, which causes the periodicity, and because of the aperiodic nature of this sequence, that would become a continuous one. So continuous periodic spectrum we would get from this 1D DTFT. So if we extend that 1D that is DTFT to two-dimensional space, that is called, here it is called discrete space Fourier transform. That is same as DTFT. Here it is a space, so instead of a time in the 2D, so it is space Fourier transform. So DSFT mean here DTFT only. So x of omega 1 comma omega 2, that is extended here. So another notation for this is also x of j omega, or x of j omega 1 comma e power j omega 2. This would also when another notation commonly used. N1 is summing over minus infinity to plus infinity, and N2 also for minus infinity plus infinity. X of N1 comma N2 is a sequence which is aperiodic and discrete, e power minus j omega 1 N1 and e power minus j omega 2 N2. For this, multiplying this, that you would sum it over for the region of support. So you get the 2D DSFT, and inverse DSFT is also this to get back the sequence from it, 1 by 2 pi square. Omega 1 is varying from minus pi to plus pi. From the spectrum, e power j omega 1 integrated, because it's a continuous spectrum, integrated from for the limits of minus pi to plus pi in both the directions, get the signal back. This is inverse 2D DSFT. So what are the properties which is very much useful to do the analysis? So if we take a sequence x of n, 2D sequence x, and its Fourier transform, that is DSFT, is x, capital X, and for the small y, another sequence, and its DSFT is capital Y. This is, then we know that this is Fourier transform is that linear. So superposition and homogeneity can be applied. So a into x of n1 comma n2 and b into y is a capital X and b capital Y. So it's linear, and the convolution we learnt in 1D, and this is linear convolution, x convolving y in the 2D sequences would give x into y, that is the multiplication of x and y. So this is a linear convolution, what we mean. So if you know the Fourier transform of DSFT of x and DSFT of y, simply multiplying that would give the convolved sequence DFT of this here, DSFT, and then the multiplication, when the signal is multiplied in the time domain, that is equivalent to convolution. This convolution, we should note that this is a circular convolution, not the linear convolution. So in the previous case, in the time domain, if it is a linear convolution, and that results in a multiplication in the frequency domain, whereas in the if it is multiplied in the time domain, this is going to be a circular convolution. It's 1 by 2 pi square. The integration is x, y, omega 1, and theta 1 and theta 2 are replaced like what we do it for the k or a different parameter. So it's an equation of this circular. So we'll do that relation between linear and circular convolution through this Fourier analysis later. And the separable sequence, it is very important property that we keep seeing that everywhere in the convolution. If the 2D signal is separable, then how we are extending this 1D signal processing concepts to the 2D. So similarly, if x of n1 comma n2, this one sequence is separable, that is a 2D sequence is separable, you can write it in terms of the product of two sequences, then it's Fourier DSFT is x of omega 1 comma omega 2 is the DSFT of the product of individual sequences. So x1 and x2. So it's easy to perform the 2D DSFT. If the sequence is separable, you can use the DTFT of individual sequences and get the product of that. Also the shifting sequence, shifting in time domain and shifting in frequency domain. So shifting in time domain, that is n1 minus m1, the n2 minus m2, or this can be n1 plus m1 and n2 plus m2 if it is in the n1 and these are negative values. So the DSFT is x of omega and omega 2 is just multiplied with the shift, like in the shifted sequence Fourier transform. He had seen this property. The shifted sequence is e power j omega 1 m1, the shift, and this is m2. And this is time domain shifting the sequence, and if that is the frequency domain shifting. So x of omega 1 minus v1, omega 2 minus v2. So this frequency is shifted. So here in that case this would come in the sequence x n1 comma n2, where it is multiplied with e power j v1 n1, e power j v2 n2. Okay, so you can see the difference in the time domain shift and the frequency domain shift. Also the initial value and DC value theorem we can get from the spectrum, 2D spectrum. Can we get the initial value of the 0, 0 value of the time domain sequence? That is 0, 0 can be obtained from by integrating it over minus pi to plus pi with the omega 1 and omega 2. This is the initial value. Supposing you have the sequence, can we get the DC value? That's what we are doing. That is summing up. In 1D we had done in the previous example, summing up the values, all of the discrete sequences. So in 2D similarly, n1 and n2 spreading from minus infinity to plus infinity, you can sum it over to get the DC value of it. And the Parseval's theorem, which is useful to just to know that if x and y are two sequences, x and y is its complex conjugate, multiplying them and sum it over, that is here, then is equal to getting this DSFT and complex conjugate DSFT essay. That means it's, we would also say that for a discrete sequence of real, its energy of x of n1 comma n2 is equal to the coefficients what we get in the Fourier domain, the spectrum. This energy is preserved both in time domain and frequency domain. So these are equal, and there is no loss in this case. So that's the meaning of this Parseval's theorem. So we can find the coefficients and its squares would give the whatever in the frequency domain, it's equivalent to the square of this, and sum it up in the time domains and energy. So energy is possessed in the coefficients. So we take the DSFT example. How do we compute for an impulse response which is given h of n1 comma n2, or considering this as a filter, or how to get this frequency response? So h of omega 1 comma omega 2. So this is a sequence which has the region of support from n1 varying from minus 1 to plus 1, and n2 is also varying from minus 1 to plus 1. So these are having 1, 2, 3, 4, 5 values, samples in it. So taking the DSFT, 2D DSFT, n1 minus infinity to plus infinity, because this region of support is restricted to minus 1 to plus 1, and similarly h2, in this case h is in the n2 direction also minus 1 to plus 1. So summation is limited to minus 1 to plus 1, h of n1 comma n2, e power minus j omega 1 n1, e power minus j omega 2 n2. So this is the DTFT formula which is extended to 2D. Here it is called the discrete space Fourier transform. So substituting n1 and n2 different values, n1 n2 minus 1 and minus 1, so is this n1 and n2 0 0, yielding this in this equation, and n1 n2 1 1 gives this minus 1 and 0, and similarly 1 0 and 0 1 would give, and 1 minus 1 and minus 1 1. So the all combinations of 0 minus 1, n1 and n2 are satisfied in these combinations. So substitute those values, what is h of minus 1 and minus 1 here, and some of them doesn't exist, n1 minus 1 and n2 minus 1. So this would be 0, h of 0 0 0, and h of 0 0, this is 1 by 3, and so on. For example, 0 0 1, n1 is 0 and n2 is 1. So this value substituted over here, and minus 1 comma 1, n1 is minus 1 and n2 is plus 1, so it's not there. So the sum of the values are 0. So substituting these values from here, so this is 0 0 and 1 0, index is known at this stage here, and here minus 1 comma 0 and 0 comma minus 1, the indices are known here. So substitute those h, corresponding h here, and you would get this values. H of omega 1 comma omega 2 is simplified 1 by 3, 1 by 6, and these 1 2 3 5 samples exist in that, others would become 0. So combining these two components and these two components, and this can be written as cos 2 cos omega 1, and similarly this is 2 cos omega 1. So we get 1 by 3 cos omega 1. So the common term can be taken as 1 by 3 cos omega 1, 1 by 3 cos omega 2. So the impulse response are of the sequence, the system impulse response is this, or this 2D sequence is x of n1 comma n2 or h of n2, whose frequency response is h of omega 1 omega 2 is this. So we can obtain the frequency response of this signal 2D sequence by using this DSFT. And if you plot this, this is a plot of sequence in the time domain. If you plot it in the frequency domain, then it would be omega 1 omega 2, and that is 3D view, h of omega 1 omega 2. How this function is varying with respect to omega 1 and omega 2 is shown as a surface plot. This can be taken as a filter which has this magnitude high here, and it is the slope, it is filtering out, these values are less in this here, these corners. So it can pass only the frequencies around this region, and it can attenuate these frequencies here. So it is a frequency response of this, it can be considered as a filter. Now if what we had done in the previous case, the impulse response we had taken, we directly applied this 2D DSFT. Suppose the sequence h of n1 comma n2 is separable, then this 2D sequence can be written in terms of two 1D sequence, product of two 1D sequences, h1 n1 and h2 n2. So how to get this h of n1 n2 values from this h1 and h2 from h? We have seen already this matrix, square matrix, and it should be determinant 0, it is non-invertible, and there are many n minus 1 solutions for n cross n matrix. So take the dependent column, here dependent ones, 1 minus 1 3 minus 1, or it can be written in terms of minus 1 3 minus 1, so column and row vectors. Or this is not the only way, it can be even 1 minus 3 1, and then the rest of this also. So supposing this is one case we take, minus 1 3 minus 1, if you multiply the two, get this matrix. So here 1 minus 1, and if this is a common, then 1 minus 3 1, this rows getting repeated. Okay, so you'll have, this would give, so what are the two, h and h1 and h2, h1 and h2 will be in this fashion. So we should note down the origin here, which is the index corresponding to 0 0 0 1 1 0 and 1 1. So that can be obtained from the sequence what is given over here. This is 0 0 and 1 0, and where we write it 9 is equal to, should be 0 0. That index needs to be taken care in the matrix as well. So we got this h, that is separability concept, to get h and 2h h1n and h2 n2, and then compute the DTFT or of the individual 1D sequences now. So it is simplified now. Instead of having the 2D DSFT, this is the formula for this 1D DTFT, h1 n1, which is e power minus j omega 1, and it is existing in certain values of, if you take the one, it is n equal to minus 1 and 0 and plus 1. Okay, so there are n1 values, and you simplifying 3 e power j omega 1 here, and this would go e power minus j omega 1, and you get this from here. So the simplified expression of h1, we got it, that is in the frequency domain. We can further simplify it for a cost expression, cost of omega 1. So we can plot this separately as well. This is one filter, and taking the H2, that is another sequence, 1D sequence, compute its DTFT. So DTFT results in similarly a sequence 3 minus 2 cos omega 2. Okay, so now H1 and H2 we have, so the separable sequence. So what is the property we had? If it is separable, this 2D DSFT, it's equal to DTFT of the individual sequences. So 3 minus 2 cos omega 1, 3 minus 2 cos omega 2. So we can have the product of this. So we computed the DFT for 1D and 1D, and then take the product, which is equivalent to computing the 2D DSFT. So separability concept, we can see how it is simplifying the process. So this is same as the expression which we got in the previous example. So if we plot it with respect to omega 1 and omega 2, this is the plot. This is not the, I mean, here we have, you can see the not as a good filter. We'll see, consider some of the filters which are having the region of support in the fashion what we had taken. Those filter signals can be separable also. So it's just a surface plot which shows that omega 1 and omega 2, how is while varying both of them, and how h of h varies. This is the frequency response again. To obtain the frequency response of 2D sequence through 1D DTFT, that is because of separability concept. So we take an example of the moving average filter. So the moving average filter in 1D, the equation of this is y of z by x of z is 1 minus z power minus n by 1 minus z power minus 1. So the factor 1 by n is used. So if we take the block diagram representation of it, if this is x of n, meaning this cross multiply it or get this, write this in terms of in the time domain equation. So you get y of n is y of n equal to y of n minus 1, 1 by n x of n minus x of n minus n from this transfer function. So moving average filter we had seen already in the 1D introduction. So the equation is y of n minus y of n minus 1, right, plus 1 by n x of n minus x of n minus 1. So this portion is actually called the comb filter. So we will discuss this a little later as a comb filter separately. And this one is an integrator you can have, and 1 by n get the y of n here. So what is the function of this filter? It's taking n samples and average it and give the average value. So that n sample window can be slided over one sample at a time, or n samples at a time, whatever the samples you want to, this basically one sample at a time, and then take the next window sample and average it. That's why it is called the moving, and then slide it once and take the n samples and take the average of it to get the output. So here x of n is delayed, that means this n number of samples are there, capital N number of samples, and then take the average of it, sum it over and take the average of it is the y of n. So this is the expression of the time difference equation of this moving average filter. Now the case of in the frequency domain, in the z plane, how does it look like? So if you take this transfer function which has one pole, and this is n zeros that we had also seen, then this n zeros are equidistant. If you solve it, equate it to 0 and get the n positions. So this would give the n number of zeros. N can be 8. Here it is given 8. So n if n is 8, then n number of zeros and one pole which is equal to 1, it's here. So this pole cancels the 0, so that this frequency response is high. Whenever there is a pole, that gives a frequency response high, which is extracting only the DC from it, or the other things are not taken into account. So this is giving the if you pass a signal which has other frequencies as well, so this would extract only the DC from it. This is a filter which is used to calculate the average of n number of samples, or if you have the multiple frequencies, it can give only the DC from it. So this is a z-plane pole zero diagram. So now we take this 1D moving average filter to 2D. So what is the 2D sequence for it? That is, because it's a 3 by 3 kernel, the kernel length is important. That depends on n is 8 there, and it can be n number of samples, that is 3 by 3, total is 9. So that should be divided by 9 here, 1 by 3 into 1 by 3 in n1 direction and n2 direction. So there is, it is multiplying the, as it move it over the signal, it would multiply those values and then sum it over and divide by 9. So that's how it computing the average of that signal. So this is in the 2D. So how this signal, 2D signal, is represented: n1 1 by 9, all the values are 1 by 9. You can see this is 0, 1 represents 0 comma 0, index should be matched with this, and plus 1 and minus 1, similarly here plus 1 and minus 1, n1 and n2 values. So now taking this average filter, can we get the frequency response of it? What is the filter response? So taking the 2D DTFT, or the case of DSFT here, space transform, h of omega 1 omega 2, n1 restricted to minus 1 to plus 1, similarly n2 also restricted to minus 1 to plus 1, h of n1 e power minus j omega 1 n1 into e power minus j omega 2 n2. So substituting these values here, n1 0 0 1, here 1 plus minus 1 and minus 1, so all values of n1 n2 available sequences. So it's only going to give 9 values, and the expressions associated with n1 and n2 will give n1 1 1 e power minus j omega 1. If it is minus 1, it is going to be e power j plus omega 1, like what we did in the previous example, and simplify it, we get this 1 by n, 1 plus 2 cos omega 1 into 1 plus 2 cos omega 2. We have splitted it here for a reason, but this can be, you would get the expression as not in this fashion, but we have separated it because this, if this sequence is separable, then we can, as we did in the previous case, then we can do the 1D DTFT of H1 and H2 separately and multiply them to get the 2D DSFT. So now see this, take the sequence, and then it is separable. So we will test the separability condition, taking this is determinant is 0, it has the dependent rows and columns, those ways that we had already known for testing the separability. So taking this as dependent rows, we can write it in the as a product of these two vectors to get this. Now 1 by 9 can be split among these two as well, 1 by 3, 1 by 3, or you can keep this 1 by 9 as such, and we can work in that for 1D separately, 2D separately, and this is going to be a constant which can be multiplied later as well. So H1 N1 and H2 N2 is the product of this, is due to the separability. So, and if the impulse response is separable, then only we can go through this process, otherwise we need to compute this 2D DSFTs, I mean in the straightforward way. Like this, we are simplifying the way in which that 2D can be done through 1D. So from the properties, we observed this individual DTFTs is the 2D DSFT. So take the individual DTFT, that is 1 by 3 e power minus j omega n1. This is a constant which can be pushed outside the summation, and you give here n1 value varying from minus 1 to plus 1, get the 3 terms, and these 2 terms can be combined to make the cos 1 by 3 1 plus 2 cos omega n. If you just refer it to the 2D h of e power j omega 1 e power j omega 2, or h of omega 1 omega 2, that is also equally valid notation. This is for one part is here, and then second one, similarly for the second h2 of n2, if we do it, h2 e power j omega 2, that's going to be 1 by 3 plus 1 by 2 cos omega 2. So we get this sequence as well. So now the h of e power j omega 1 and e power j omega 2 is product of the sequences 1 by 3 1 plus 2 cos omega n and 1 by 3 1 plus 2 cos omega 2. So it's going to be 1 by 9 here. You can see the 2D one which we got 1 plus 2 cos omega n and 1 plus 2 cos omega 2. That is same as what we obtained through the 2D DSFT. So from this, what we had learned is that 2D DSFT, which is extended from 1D DTFT, in which where it is called the time t, discrete time Fourier transform. Here in 2D it is discrete space Fourier transform, and using the separability concept we can use the 1D DTFT to compute the 2D DSFT through the example. So this is possible only if the sequence is separable, and we have gone through this, a few properties which were useful. One among this is linearity, and the multiplication. Multiplication in time domain is convolution in the frequency domain, and if this is convolution in the time domain, okay, so then that's going to be a multiplication in the frequency domain. So we would see that linear convolution and the circular convolution, so these are two different things in the time domain as well as in the frequency domain. So we would be dealing those different when this convolution would be equal, and if what about the length, what is the condition at which this length will be equal, then these two sequence, the resultant of convolution 1D and 2D will be same. So the one which we had already seen in the 1D case can also be extended to the 2D case. So but the difference between the case of 1D convolution or the linear convolution and the circular convolution, what we did, what are the differences in 2D can also be obtained through a few examples. So obtaining the frequency response is the way in which we had demonstrated here with few examples. We'll extend this one also, that two-dimensional DSFT. For instead of DSFT, can we do the DTFS, that is discrete time Fourier series, what we did in the 1D case. Also discrete time Fourier transform, which is a DSFT, can we have the DFT for it, that is 2D DFT, which is the sampled version of this DSFT or DTFT. So these relations we will do in the next lecture. Thank you.